In a modern enterprise environment, data never stops moving. The concept of static information has been replaced by a relentless stream of continuous events. This chart illustrates the performance baseline. Throughput must hold steady over 50,000 transactions per second, while latency is confined to a 1,000 millisecond ceiling. Breaching that triggers immediate failures. Milliseconds of delay cascade, destroying downstream systems waiting for stalled records. Legacy pipelines delegated tasks across a distributed system. Producers push data to a central Kafka cluster, relying on Zookeeper for coordination and an external Spark cluster for computation. The fatal flaw is physical distance. Every external network jump introduces severe latency and potential failure. To maintain performance at massive scale, Kafka operates as an autonomous, self-governing compute engine. Building a reliable real-time pipeline requires mastering Kafka's internal mechanics, specifically how it governs its own control plane and compute plane to mathematically guarantee performance. For years, Kafka required a completely separate system, Zookeeper, to act as its centralized manager. Zookeeper held all the cluster metadata and directed the leader elections for data partitions. Node failures created a massive penalty. The cluster couldn't heal instantly. It paused to query Zookeeper for leader elections. Centralized metadata imposes a strict scaling ceiling. A single Zookeeper bottleneck limits the partitions a cluster can support before performance degrades. Deploying and maintaining two distinct distributed systems also creates severe friction in cloud-native environments. Containerized tools like Kubernetes struggle to seamlessly coordinate the intertwined life cycles of both platforms. As long as metadata coordination remains tied to an external network dependency, true horizontal scaling is architecturally impossible. This schematic details Craft, or Kafka Raft. This architecture removes Zookeeper entirely, unifying metadata management and leader elections within the Kafka brokers themselves. The external database is replaced by an internalized controller-broker quorum. Craft operates on the Raft consensus algorithm. Instead of querying a centralized source of truth, the controller nodes achieve distributed agreement internally, requiring a majority vote to lock in decisions. Under this architecture, metadata is treated exactly like a standard Kafka event log. It is appended sequentially and distributed directly to the active brokers. Zookeeper relied heavily on dynamic elections, which could become unstable under load. Craft defines its controller nodes via static configuration files, establishing a predictable and highly reliable quorum. The resulting performance payoff is immense. System recovery times drop from multi-second network delays down to sub-millisecond internal operations. Internalizing the control plane grants Kafka true architectural autonomy. By removing the external coordination bottleneck, the primary physical barrier to infinite partition scaling is eliminated. Moving data autonomously secures the transport layer. However, that efficiency is lost if the records still have to be exported to an external cluster for processing. The legacy compute model relied on batch processing, slowly pulling static datasets on a schedule. Modern architectures require stream processing, executing logic on individual records the millisecond they arrive. Waiting for batches guarantees latency penalties. Event-at-a-time processing keeps pipelines clear. Kafka Streams solves this problem natively. It embeds the compute layer directly inside the Kafka ecosystem. A Kafka Streams application is architected as a directed acyclic graph, establishing a one-way processing topology. Data enters the source processor from a topic, flows through stream processors for transformations, and the sync processor writes finalized data outward. Executing logic directly on the stream entirely bypasses the need for heavy external ETL clusters. This drastically reduces overall architectural complexity. Stream processing introduces a critical computational challenge. How do you maintain a running total, or state, when the data flowing in never actually stops? This layout demonstrates how Kafka Streams handle state through two abstractions. First is a K-stream, acting as a stateless, append-only log of facts. Second is a K-table, a materialized view that actively updates itself by overwriting previous keys. A continuous K-stream can be programmatically grouped by key and counted to output an accurate static K-table. To guarantee that this state is not lost if a node crashes, the table is persisted locally using an embedded RocksDB instance. Developers dictate this logic using either the declarative high-level DSL for rapid builds or the low-level processor API for absolute granular control over individual nodes. By utilizing K-tables and RocksDB, Kafka achieves database-tier state reliability locally, completely eliminating the network latency of querying an external database. These two internal evolutions combine to create a unified blueprint for a self-governing data system. On the control plane, external Zookeeper bottlenecks are eradicated, replaced by an internal Raft consensus that recovers from failure in milliseconds. On the compute plane, the massive latency of external batch clusters is removed, replaced by embedded, stateful stream processing operating directly on the data. This exact architecture allows enterprise systems to hit rigorous performance baselines, easily sustaining over 50,000 transactions per second, while keeping 99th percentile latency safely beneath 1,000 milliseconds. An enterprise-grade cluster is a high-availability distributed compute system, where reliability is a direct result of precise, ground-up control over every internal plane.